All right, so we're in section 8.6, our last section for the chapter.
Our test is on Friday. What is that on?
8.1 through 8.6. So we're going to talk about area and volume ratios today. So far we've been comparing when we compare similar figures. We've been comparing the sides. We've been comparing the altitudes, different lengths. We want to figure out if we have two similar shapes, how their areas, and if we have two similar solids, how their volumes compare. So we want to figure out the ratios of their areas and volumes if they're similar. So one thing that we already know is that if figures are similar, the lengths are in the same ratio. So that's what we've been using pretty much the entire chapter, is we know we have similar figures, so we compare the lengths and we say that the ratios are the same. Now when we're talking about lengths in similar figures, a length can be lots of different things. Length can be the side length. Lengths can be the perimeters. Anything that's a length, a perimeter, a radius, a height. Anything that's a length is going to have the same ratio between similar figures. So if we have similar figures, their lengths are always in the same ratio. And that can be any of these things, and it can be any, as long as it's a length, and we're comparing lengths on two similar figures, the lengths are going to have the same ratio. So that can be side, perimeter, radius, height. It could be the length of a diagonal. It could be a median that we talked about the other day. It could be an altitude. Any of those things that are measures of lengths are going to have the same ratio. What we're interested in today is the area and volume ratios. So let's talk about the area ratio first. If we have similar figures that have a length ratio so if their lengths in the ratio A over B and this is an A, not a 9, then their areas are in the ratio A squared over B squared. So to get the area ratio from the length ratio, we square it. So that's what this is telling us. Square the length ratio to get area ratio. And it kind of makes sense because when we think about our units on length, our units for length are just units, inches, meters, whatever. But the units for area are square inches, square meters, square units. So it makes sense that to go from length to area we would square. So it kind of fits in with what we've already done. So let's take a look at an example using this idea. Is everybody good with what we have here? Okay, so our example, we have a triangle. So this looks kind of like our opener. Here's our triangle, and we have these parallel segments, and I'm going to label this ABC. D and E. And we know this is 4 and that is 5. We want to find the ratio of the areas of triangle ADE and triangle ABC. So we want to find the ratio of those areas. Now we know that the triangles are similar. We know that triangles are similar. These parallel lines tell us that the sides are divided proportionally, so our triangles are similar. So what is our, we want the area ratio. What is our length ratio? What's the side, what's a length that we can use from the small triangle? 4. And what's a length that we can use from the big triangle? 9. These two added together is the side of the bigger triangle. So the length ratio is 4 over 9. To get our area ratio, we square this. So that's 4 squared over 9 squared equals 16 over 81. So our area ratio is 16 over 81. That's all the problem asks us for, to find the ratio of the areas of ADE and ABC. Pretty easy, right? Now what if the problem had asked us, rather than the ratio of the areas, what if it had asked us the ratio of the perimeters? Is a perimeter a volume, an area, or a length measurement? Length. Perimeter's length. So what would the ratio of the perimeters of the triangle be? What's our length ratio? 4 over 9. Perimeter is a length, right? So the length ratio is going to be the same, no matter what length we're talking about. So the ratio of the perimeters would also be 4 over 9. The ratio of the altitudes would be 4 over 9. The ratio of the medians would be 4 over 9. Any ratio of lengths between the big triangle and the small triangle would be 4 over 9. As long as we're comparing lengths, they have the same ratio. When we move to a different measurement, the area, then we have to square it. So as long as it's a length, the length ratio is the same for any length we're talking about. Now, we need to figure out how we go the opposite direction. If we have the area ratio, how do you think we go to the length ratio? Square root it. The area ratio is squared. To undo the square, we square root it. So if we have the area ratio and we want the length ratio, we have to square root. So let's write that down real quick and then we'll do an example. So to go from area ratio to length ratio, we square root. That undoes the squaring. So let's look at an example of that. We have two spheres. With a surface area ratio of 144 over 159. Sorry, 169. What is the ratio of the radii? So the first thing we need to know is two spheres. Are two spheres always similar? Yeah? Because we said for shapes to be similar, they had to be, the kind of our loose definition was the same shape but a different size. So can two spheres ever be different shape from each other? No, they're always, a sphere is a sphere, right? So two spheres are always similar. So two spheres are always similar. And it tells us our surface area ratio is 144 over 169. So that's our area ratio. Our area ratio is 144 over 169. To find our length ratio, radius is a length, right?
Yeah.
Radius is a length. Length ratio is the square root of 144 over the square root of 169. And that gives me 12 over 13. So to go from, if we have similar figures, to go from an area ratio to a length ratio, we take the square root. Questions on that? All right, let's talk about the volume ratios. So just based on what we know about volume and area and length, what would you guess that we do to the length ratio to get the volume ratio? Anybody have a guess? Julian? Cube it. Perfect. So to go from a length to a volume, we cube it. Our units for volume are cubic units, cubic inches, cubic meters. So to go from a length to a volume, we cube. So what we're going to write is if two similar solids have a length ratio A over B, the volume ratio will be A cubed over B cubed. So we cube the length ratio to get the volume ratio. Just like we cube a length to get the volume of a figure, to get the volume ratio, we cube the length. So let's look at an example of using this. We have two spheres. The radii are 5 centimeters and 7 centimeters. And we want the ratio of the volume. So radius is a volume, an area, or a length. Radius is a length. So let's write our length ratio. What's our length ratio going to be? 5 over 7. It's just the ratio of the two radii. The length ratio is 5 over 7. The volume ratio, we cube this. 5 cubed over 7 cubed. And when we cube 5 and we cube 7, we get 125 over 343. So the volume ratio is going to be 125 to 343. Questions on that? So let's think about what we would have to do then to go the other direction. What if we have the volume ratio, we have this ratio, and we want to find the length ratio? What are we going to have to do? Undo the cube, and how do we undo a cube? Cube root. To go from a volume ratio to a length ratio, we take the cube root. So to get length ratio from a volume ratio, we cube root. So let's look at an example of going this direction. We have similar prisms. And their volume ratio is 64 over 125. We want the ratio of the base perimeters. So we know the volume ratio is 64 over 125. We want to figure out the ratio of the base perimeters. Perimeter, a measure of volume, area, or length. Perimeter measure of volume? No? So are we asking about the area of the base? The perimeter of the base. The perimeter, how do we find the perimeter of a shape? All the sides? So if we're talking about the sides, are we talking about an area, a volume, or a length? Length. So perimeter is length. Perimeter equals length. So to get the length ratio, doesn't matter what length ratio it is, we take the cube root of 64 and the cube root of 125. So our length ratio equals the cube root of 64 divided by the cube root of 125, and we get 4 over 5. Any questions on that? Now, what if this problem had asked us to kind of follow up on what Jalen said? What if the problem gave us this volume ratio, and instead of the ratio of the base perimeters, it wanted us to find the ratio of the base areas. How would we go about doing that? Square the ratio of what?
4 and 5.
4 and 5. So Nick says square the length ratio. That's exactly right. To get area, we square the length ratio. So if your problem gives you volume and asks you for an area ratio, you need to find your length ratio first and then square that. So that's kind of a two-step problem. If you have the volume ratio, to get the area ratio, you need to find the length ratio first and then square that to get your area ratio. Questions? All right.
Can I use the restroom?
Yes.